Hello grade 12s, welcome to my channel. Let us have a look at this question paper. It was a request by one of you guys who support my channel, and I hope this finds you well and perhaps still awaiting your physics paper 1. But if that is already over, then perhaps it can help for the preparation of the next exam, be it the trials or the finals or upgrading next year. Okay guys, we need to read instructions carefully, making sure that we understand all the actions necessary to be taken, and we need to commit instructions like this, and that telling us that we need a minimum of 2 decimal places. Given a chance to explain, we need to be as brief as possible, but remember, anything is applicable, from a formula to some calculation or just a word explanation or a mixture of all these three. All right, so let's go through the MCQs. Now 1.1 asks which one of the following has the smallest inertia. Question is, do we ever quantify inertia? Well, in most textbooks it's just explained rather than quantified. But what do we know? Inertia in high school physics is related to linear motion. Right? And in linear motion it is a function of mass. So this just simply means we just have to focus on the mass to quantify here, and such that the greater the mass, the greater will be the inertia. Right? So this is what we need to understand, okay? That inertia is a function of an object's mass, and essentially it's all about resistance of change in its state of motion. Okay, so it means a heavier object would be much difficult to change its state of motion, isn't it? Take for an example a wardrobe full of clothes. To lift it is not so easy, right? Yeah. But a box that is empty, you can lift it with just one hand. So it's just about how well it can resist. And all this depends on the object's mass. So we can clearly see that a 35 kg girl running upslope would need much less, opposition force than a 45 kg boy. Here, the issue of sliding on a frictionless ice or whatever doesn't matter, because if they start moving, to stop them is going to be quite an effort, isn't it? And here we have a box of 296 newtons rolling on a rough surface. Now this is the weight, right? But now we know that weight is mg. So this means 296 is equal to mass times 9,8. And therefore we know that the mass here is going to be the ratio of the weight, which is 296 divided by 9,8. This gives us a 30,20 kilograms. Okay? So that's the smallest so far. Same here. Weight is mg. So this is 512 equals m into 9,8. So it means the mass here is going to be 512 divided by 9,8 gives us 52,24 kilograms. Okay, so which one has the smallest mass? Is C. Okay, great. Next question says a man standing on the Earth's surface has a mass of 80 kilograms and a weight of 784 newtons. If he is put in a satellite floating freely in space far from Earth, his mass and weight will be. Of course, his mass is a constant. Right, so it won't change. So we expect an equal to, and these options are already out. Now let's see, what is the scenario here? Let's say there is our Earth, and there is our center of the Earth, and we have the man sitting on the Earth here. Right, what is the difference between, in fact, what is the distance? It is the radius of the Earth. But when we take this man and place him on some satellite in space, so there he is. All right. Now, what would be the distance between the center of the Earth and the man? Of course, this is going to include r, the radius of the Earth, plus this distance, which we can call d. So this means the farther you are away, what happens? So we know that weight Fg is big G m Earth times m of the body divided by r squared. Now, we can clearly see that there is an inverse proportionality between the weight and the square of the distance. And now, with this situation, it means the distance would increase, and that means r squared will increase, and so the force should decrease, meaning it's going to be less than on the surface. So we understand that this would be the answer. Okay, so this is on the principle of universal gravitation, right? Newton's law of universal gravitation, meaning the force is inversely proportional to the square of the distance. If the distance increases, the force decreases. If the distance decreases, the force will increase. Okay, so 1.3 says two identical balls, A and B, each with mass m and traveling with speed v meters per second, are moving towards each other. So we can choose motion to the right as positive and that to the left as negative. So this is going to be plus v, this is going to be minus v. Okay, so it says the balls have a head-on elastic collision. So what do we know about an elastic collision? We know that EK is conserved. What is conserved? It means it remains constant. Or constant means unchanged. Okay, just a bit of English there. Okay, so which statement is correct? The balls will stick together, perhaps. We're not sure. The total kinetic energy of the balls after collision is mv squared. Is that so? Let's see. EK before is going to be half mv all squared plus half m minus v all squared. We sort this out. It's half mv squared plus half mv squared. This is going to be essentially 1 mv squared, or is it just mv squared? So this is true. The total kinetic energy of the balls during the collision. Now, during collision, it's a different story. There's going to be sound, there's going to be friction, maybe heat, or even deformation. So this cannot be. It's unlikely, okay? Again, it's one of those we cannot really put it together nicely. It says the total momentum of the balls before the collision is non-zero. Is that so? We can calculate it. So we know that P before is going to be mv plus m into minus v, right? Right. Which is going to be equal to mv minus mv. And this is 0. So it is 0. So the statement is untrue. So the best would be B, although we don't know about A and C, but they don't seem to matter anyway. But they are there to confuse us, I suppose. So 1.4 asks that rifle bullets, or at least states that rifle bullets, each with mass x kilograms, are fired at the rate of n bullets per second, right, on a wall. Right, it says the magnitude of velocity of each bullet is v meters per second, and they rebound with the same velocity. So, of course, we can choose motion to the right or towards the wall as positive, so it's going to be plus v. So if we have a wall, this is some vertical barrier on a horizontal distance kind of a situation. So this is the bullet. So it's going in this direction. It will hit the wall and then rebound. All right. So this is going to rebound at minus v, and it's going at v. Right. And the mass here is x kilograms. Okay. So this is more of the impulse story here. The gravitational acceleration is g meters per second squared. The question is, do we really need g here on horizontal motion? Not too sure. Well, if this was to be a vertical situation, but then we wouldn't say this is the wall. If this was vertical issues, this would not be called the wall, but the roof or the floor, depending on the direction of the bullets. So for me, I'm convinced this is the scenario at hand. So the question asks, the average force in newtons exerted on the wall will be. So we know we are going to use the impulse momentum formula. Right. So we will have F delta T is the mass, and this is going to be the change in the velocity. So F is going to be x into minus v, right? So this means our F is going to be x into 2v minus 2v over delta t. Therefore, our F is going to be essentially x minus 2. Okay, I'm thinking, why do I want to struggle? I can just do it. So this is going to be minus 2xv over delta t. Right, so this is the force exerted on the bullet by the wall, but using Newton's third law, we know that the force is going to be exactly on the wall, is going to be the direct opposite of this. So this is going to be 2xv over delta t. But now the problem is the collision time was not given to us. And by the way, we need to appreciate something here, that this is for each bullet. But now there were how many bullets? N bullets, and these forces are additive. So we multiply by n. So what do we get? We're going to get 2xnv over delta t. Now we don't know about the collision time, it was not stated. So we have a bit of an issue here. But there's something we may want to entertain and say, we know though that velocity over time gives us acceleration. Could it be equal to g? So the question is, the statement said gravitational acceleration. Does it really play a part here? If somebody was saying their acceleration of the bullet is, we would understand. Okay? We would understand. So this is a bit questionable for now, but this is something to consider. Right, let's just look at the options and see what looks like what we want. So we have x and v here. So this means basically the 2 is out, so it means the collision time was 2 seconds. But the question is, who said that? So this is unlikely. So this is x and vg. The moment we multiply velocity and gravitational acceleration, it's already ridiculous. This is 2x and v. Now this is when it's suggesting that the collision time is 1 second. 1 second is somewhat stated, but rather vaguely. We're like, okay, hold on. This is 2x and the moment we multiply the velocity with the gravitational acceleration, for me, does not make sense. So I would accept C. It looks more like what we have on the numerator, assuming, of course, that the collision time is going to be 1 second. That looks a bit closer. This scenario here doesn't make any sense because g here is multiplied with the velocity, and yet if we put g or acceleration, it should replace v over t. We should be having 2x and g, so to speak. So not vg. So yeah, I guess this is just those questions that are meant to create chaos in the brain. But it is certainly an abuse because it's an incomplete question, which is rather not recommended, I suppose. But again, it's all about, can you find the best answer over just the correct answer? Because sometimes it's not exactly the correct answer that the examiners are looking for. It's just to say, can you gravitate towards something better when there's nothing else better? Of course, guided by the principles to some extent, I suppose. Okay, 1.5 says a boy and a girl stand on the edge of a cliff of height h. The girl throws a stone vertically downwards with speed v towards a river. Simultaneously, a boy throws a stone vertically upwards with the same speed v away from the river. So basically, if we choose up as positive, so it means this boy is going to really have this launched at plus v, while the girl is launching this at minus v. Okay? But now the stone that is thrown upward will reach maximum height, where the velocity is 0, and come back down. And when it reaches the same position that it came from, it's going to be at exactly the same magnitude but negatively directed, and the stone will go on to reach the ground. But now of note is that these two leave the same height h with the same velocity, irrespective of how the other one went about it. It took the long route, but it came back down. All right. So this is the idea that we have. And of course, assuming this is, a free fall. Okay, here comes the statement that frees us. I like it when it comes. Sorry, because if it doesn't come, then we become a joke. So we can see that these two are actually displaced the same height h from their initial position to their final position. And they leave that very same height with the same velocity, and this is a free fall. So it means the velocity should be the same. So the velocity by the girl is going to be the velocity by the boy at the end when they hit the ground. Okay, so that's the idea. Yes, the stone by the boy is going to arrive later, but with the same velocity. Right, so it says, which of the following statements is true? The stone thrown by the girl will hit the river first. Yes. With a greater speed. No. Because of this, that statement is gone. Both of the stones will hit the river with the same speed. True. Only when both the stones have the same mass, it is not necessary. This is independent of mass, to be honest. So, no, because of that. The stone thrown by the girl will hit the river first. True. Because it has a smaller displacement. Not true. Now, obviously, once we eliminate those successfully, whatever D says should be correct. But we need to be careful, though, that we are not making a mistake in A, B, and C. So both the stones will hit the river with the same speed. Acceptable, regardless of the height of the cliff. True, because even though the height may be high or short, it doesn't matter. If they leave that same height, whatever it is, with the same velocity under free fall, they will definitely hit the ground at the same speed. So I would accept that statement, although that one can shake a student a bit, but a proper elimination of the other three options makes it a bit easier. So 1.6 says a trolley of mass 20 kilograms moves from position P to Q along a rough track. So a rough track means there's kinetic friction for a moving object. Now at point Q, its gravitational potential energy is Y less than at point P. Okay, so if we say the EP at P, EP there should, maybe let's say it's X. So it means the EP here is going to be X minus Y. Okay, that's just what we can do there. Now its speed at point P is 2 meters per second, and the work done against friction is 60 joules. Okay, so we know friction does negative work. So again, this is the only force that seems to be doing the things here. So if we're doing work against friction, even if we did more work, it doesn't matter, but the one that balances friction, it means friction does minus 60 joules. Now we need to do this business. It says, now which of the following represent the magnitude of the velocity at Q? Okay, so we can do work done by a non-conservative force. It's going to be change in EP plus change in EK. Right, so we were told this is 60, but remember, it will do negative work. It opposes the motion. So EP, it's going to be basically X minus Y minus A minus X, because it's final minus initial, plus the kinetic energy here is half of 20, and the velocity here is going to be V minus the initial velocity, which is 2. Oh, by the way, this is squared, so this is V squared minus 2 squared. Okay, so we have minus 60 is equal to, there's 2, take each other out, so we get minus Y plus, so we've got 10 into V squared minus 4. So this is minus 60 equals minus Y plus 10V squared minus 40. So if we isolate the 10V squared, transpose this, it's going to be y plus, no, it's going to be y minus 20, right? We divide by 10 and take the square root, so we know that v is going to be essentially the square root of y over 10 minus 20 divided by 10 is going to be 2. Okay, but now we see that this is factorized further, so this is going to be the square root of, and in fact 1 over 10 when we pull it out, because y is isolated, so it means we pull out the 1 over 10, but 1 over 10 is 0,1 into y minus, now 2 divided by 0,1 is 20. So this is meters per second. So where is that answer? It's B. Okay, so this is one of those higher grade questions where some serious thought needs to be exercised. All right, so an astronomer observes light from two galaxies. Galaxy A is moving away. So if it moves away, we know that it's going to have low frequencies. It will appear to have a low frequency, which then means a higher wavelength, and that's what we call a red shift. Okay? And we've got galaxy B moving towards the Earth. Right. So this would mean a higher frequency, which means a lower wavelength, and we call this a blue shift. Okay, Doppler effect. It says both galaxies originally emitted light at frequency f sub 0. If the observed frequencies of the light from each galaxy, now this is the observed one. For A, that would be the red shifted, mark it nicely, which is going to be smaller than the one, and then FB is going to be the blue shifted one. Now respectively, okay, if both galaxies are moving at low speeds, okay, I don't know if this matters at all, which of the following statements is correct about their observed frequencies? Now both galaxies will appear red shifted. No. The frequency of light from galaxy A is lower than f sub 0. True, because that's a red shift. While the frequency from galaxy B is higher than f sub 0. That's a blue shift. That's true. Okay, so the statement sounds right. I don't think there's any. Let's read. Both galaxies will appear blue shifted. Not both. The frequency of light from galaxy A is higher than. No, it cannot be. While the frequency of the galaxy B is lower than. Remember, this one is approaching, so it must be higher. So definitely B. Alright, so 1.8 says two charges plus Q and plus 3Q at 3x meters away from each other when test charge Q is placed at P. Remember, a test charge, should we say, generically is positive. Okay, so we should know that. So this is a positive charge. So there will be repulsion by Q, there will be repulsion by plus 3Q. Now if this is 3x and that is x, this means this is 2x. Okay, right. So question says now, when the test charge Q is placed at P, will it move towards the 3Q charge? Will it move towards the Q charge? Will it remain where it is when the resultant force is 0? Will it move vertically downwards? This is already absolutely nonsensical. So we're dancing with those three. So we need to find out, because there will be two forces, one that is pushing this like that and one that is pushing this one like that. The question is, are they equal? or are they not equal? And which one is greater? Because the greater force will then cause the resultant force in its direction. Okay. So we can say this is force of Q. This is the force of 3Q, right? Because they will oppose each other. So we want to know which one is bigger and which one is smaller. Now, we will calculate and say find F of Q on P is going to be K Q times this charge itself over the distance between them. What was it? It's x squared. So that's it. Okay, let's compare with the other one. So the F of 3Q on this charge is going to be K 3Q times Q divided by 2x. Okay, so this implies that we will have 3 KQ times Q all over 4x squared. Now we want it to look like that so that we can understand. So this is going to be 3 over 4 into KQ times Q over x squared. And so this means this is 3 over 4 FQ. So now 3 over 4 is smaller than 1 because this is itself and this is 3/4 of itself. So let's see. 1 minus 3 over 4 is what? Is a quarter. So it means this force is going to be greater. Of course, the distance makes sense for that to be the case. But this force was quite big, so it wouldn't be so easy to ignore that it could easily balance depending on that distance working the magic. So all we can see here is that the resultant force therefore is going to be the difference, and it's going to go in this direction, and that means it's going to move towards the 3Q charge. So this is A. Again, one of those higher grade questions where some thought becomes necessary. So 1.9 says, which graph best represents the relationship between total energy transferred, E, and the electric current, I, in the heating element of a hairdryer? Alright, so what do we know, guys? We know that work is basically VI delta T generically. Of course, guys, if you don't remember these, go and check the information sheet. So what else? We can adapt this because we know that this is E now is equal to, we don't want the V part because we can connect to a higher voltage if we liked. So we don't want this. So we know that V is equal to IR. So this is going to be basically I squared R delta T. So that would be E. And now we know that the resistance is specific for a particular material, and the time duration of heating it up also would be somewhat constant if we think about it. So we can clearly see that essentially E is directly proportional. We can easily say E is directly proportional to the square of the current, because this is the relationship we want to explore. So one can think of direct proportionality and say if I squared increases, then E increases. But because this is squared, if we think about it, this equation right here is the same as the equation Y is equal to AX squared. So it's a quadratic. Of course, the constant here being the A. So when we draw this on the XY axis, it's a parabola. So this is the one because it hits the origin. So that is the answer right there. All right, great stuff. So yeah, this is coming from the origin, but this should be squared for this to be the case. So as a result, it's wrong. This one is totally wrong. This one comes from the origin. And so, yeah, this one is an inverse relationship. So this is, again, guys, what I would suggest, try to understand the equation that governs any graph that is given. And from there, try to find out which mathematical equation can you see from algebra or functions, or which function does it resemble in mathematics. You will not go wrong in knowing what the graph should look like. Alright, so 1.10 says the diagram below shows an electric circuit with an internal resistance R and the external resistance of, and the resistance of the external resistor is 2R. Okay, great. Of course, following the conventional current, it goes this way and this way, that way, and completes the circuit. Right. So, question says now, what is the ratio of the power of the internal resistance versus the power of the external resistance? Again, we know that the power formula is VI generically, but now the internal resistance has a different voltage to that of the external resistor. So we want to kill this thing. So power is going to be, V is IR times I. So we will know that power is going to be I squared R. Okay, so we know that the resistor is given, the current would be the same because we want the same thing so that we can compare the ratios. So we can calculate that, of course, the power of the internal circuit is going to be the same I squared but R. And then the power of the external circuit is going to be I squared times 2R, which means the power of the external circuit is going to be 2I squared R. Now, the ratio is going to be I squared R divided by 2I squared R. Great, so these divide and we end up with R over 2R. So it's literally the ratio of the resistors. But now we don't know the relationship between R and the R down here. So what can aid us is to factor out the coefficient here. We get R over R. Okay, so now the question says, if we look at the options, we already have a half here and there is the half. So if we are still multiplying it by something, it's unlikely to be the answer. Now, what about the other options? Now we should know that R is always less than R. Or should we say that would be the assumption? Sometimes we needed to know exactly what's the relationship, but if we think about it, an external resistor has hardly been smaller than the internal resistance, because even when building a battery, by default, we want it to have the least resistance so that we can have the most energy from that battery delivered into the external circuit. And of course, in the external circuit, it's possible that we could have a resistance just as big as the resistance in the internal circuit, but I mean, how often is that? So I would say with the assumption that this is the case, because again, this is more of an assumption than it is a general rule. But again, it's practical. It's a practical assumption, I would believe. So it means if this is the case, this is a proper fraction, right? A proper fraction is less than 1 but greater than 0. And if this is the case, then this means this ratio is going to be less than a half. So I would take that it cannot be bigger because of this parameter down here. So A is an acceptable answer, but I'm not quite comfortable with questions of this nature because they really abuse the mind unnecessarily so. But again, it could be a question of, does anyone notice that this is often the case rather than to say always the case? And so we take the common thing over the uncommon thing, right? I guess that is the message right here. Okay, guys, so that's it for the MCQs. So let's get to the long questions or the structured questions. So question 2 says, a learner drags a heavy box of 5 kilograms on a rough, dry surface across the school hall floor and with a force of 10 newtons. Right, the sketch is given. The box moves at constant velocity of 0.5 meters per second. So what does this mean? It means the resultant force is 0, which also implies that the acceleration here is 0. And what does this mean? Since there will be friction, it means the frictional force should be equal to 10 newtons as well, because then there will be no resultant force. Great. Okay, over the dry surface as we were told. Okay, define the term kinetic friction. Again, folks, this is on Newton's laws and forces. If you find yourself struggling to answer this question, it means go and revise all the definitions. But if you are doing it effortlessly, it means you're probably ready. We will just check for the sake of completeness sakes, but you're comfortable. So what is kinetic friction? So this is a force exerted between the surface and a moving object horizontally, such that the force opposes the motion of the object. Okay, of course, guys, you can read anywhere and try to find whatever definition you can find. In my opinion, I favor more of the words that can be generated by the student, because it tells me exactly their level of understanding of the subject or even the concept itself. So it's a force exerted between the surface and a moving object. Key is that it's the surface and a moving object, but this is horizontally. We need to know that. Such that the force opposes the motion of the object. I would say that is enough, guys, but again, whatever seems relevant, you can go for it. Draw the free body diagram of the box on the dry surface. Okay, easy. So we will have the normal force going against gravitational force. Here, they should be proportionally equal in a way. So we will have the 10 Newton force. So this is the applied force, which is equal to 10 newtons. We know its value. So this is going to be the kinetic friction. This is the normal force. This is the gravitational force. Of course, when you use, but I think this diagram is a bit misleading. It would be dangerous. Let's just do a cross straight up. Let's just do a cross straight up because it's going to cause us problems. All right, so this is what we expect. And of course, this should proportionally be equal in a way. Of course, guys, when using the usual symbols, there's no need to write anything in full. But when using unusual symbols, a key is necessary where each can be stated fully. So this is otherwise an easy 4-mark question. Right, so 2.3 says, what is the magnitude of friction? This is 10 newtons, right? Easy 1 mark. So we can say here 2.4 says, explain the answer in 2.3. Well, remember guys, an explanation sometimes can be a calculation. Don't be forced into showing words. Okay? So even an explanation through a calculation would be valid. So sometimes these are very nice questions if you ask me, when it is like this, because the explain part, people fixate on just using words. We can say since the object is moving horizontally at constant velocity, the resultant force on the object is 0. Okay, therefore the applied force of 10 newtons must be equal to the Fk, or you can write the kinetic frictional force. Okay, again, you can either do this in words as I have, or just show the calculation thereof. It's as simple as that. Let me show you guys so that you can see what I'm talking about. I know many of you don't take these things seriously. We know that the resultant force, we can say the force applied plus the kinetic frictional force is equal to 0 because of constant velocity. So that means the forces are in equilibrium. That's another way of putting it. So this means we have 10 minus Fk. In fact, why do we say minus plus? Remember, this is addition, by the way, is equal to 0. So therefore, Fk is minus 10 newtons. This could be a good explanation. So this knowledge that this is going to be equal to 0 is important, and the final answer, that's 2 marks. Or we can say the object is moving horizontally at a constant velocity. Once we state that the resultant force will be 0 is good, and we make the conclusion that those two forces would be equal. Of course, this is an option. So that way of saying explaining is somewhat an indirect invitation to answering this question through a calculation as well. Okay, so 2.5. It says when the box was dragged with the same 10 Newton force across a rough, wet surface in the school hall floor, the box's velocity increased to 0.6 meters per second in 1 second. It means this started to accelerate. So it means the resultant force is greater than 0 this time. And this means there's a non-zero acceleration as well. Okay. Because of Newton's second law and the issues of proportionality. Okay. There we are. So it says calculate the magnitude of the coefficient of kinetic friction experienced by the block on the wet surface. Okay. So 2.5.1. Now we've got two things first. We want the resultant force. We will get it from the applied force. And we need the magnitude of the kinetic friction, basically. So we need the kinetic friction. But we know that there is an acceleration here, which we also don't know. So from this, we need to calculate the acceleration. We know that acceleration is the change of velocity over change in time. So this implies that the acceleration is going to be the final velocity, which is 0.6 minus the initial divided by 1 second. Okay, therefore our acceleration is basically 0.1 meters per second squared in the forward direction. Right. So we've got one component. Now we need the kinetic friction. We know that also the 10 Newton plus Fk, or perhaps let's put the formula again, the resultant force equals ma. This implies that the 10 Newton force, now remember we're moving to the right, so this time we will and should, sometimes I wonder if what I am about to do is right or wrong. Yeah. So either way, guys, if we want the kinetic friction, if we just are interested in the magnitude, we don't really care about the sign, do we? So we can just say plus the Fk should be the mass, which is 5 kgs. So this is 5 into 0.1. So we can see that Fk, at times I prefer to just put the negative here so that the answer comes up positive, or you can place it positive, then the answer comes up negative. It's not a big deal. So this means that our Fk is going to be 10 minus 5 into 0.1. Basic calculations, 10 minus 5 into 0.1. We get here a 9.5 newtons, because again we wanted a positive answer, so we adjusted things as we would, but we could get a negative answer and just ignore the negative and choose the direction. So what do we say then? We know that the kinetic friction is itself the kinetic coefficient of friction times the normal force. So this implies that 9.5 is equal to mu k times the normal force. This time we are using these vertical forces now, that the gravitational force is equal to the normal force. I can go give a link. So we know that since this object is not moving vertically, those are balanced. So if they are balanced, it means this is going to be 5 times 9.8. It's going to be equal to the gravitational force. Therefore, our kinetic coefficient is going to be 9.5 divided by 5 into 9.8. Okay, so this is 9,5 divided by okay, so we're getting a 0,19. Remember, this is a ratio, so there is no unit. So of course there's a lot of work, guys, we did here, but for me the value of the acceleration is important, the value of the frictional force is important, the value of the kinetic coefficient of friction is important. For me, which formula takes the crown is the one that answers the question. The others are a means to an end. And again, calculating the normal force for me is much more important. Right, so this is how I believe the 5 marks are scored. So we've got 2.5.2. It says draw a graph that shows how the coefficient of kinetic friction and the applied force change across the dry and wet surfaces. But for me, the applied force has no relationship with the coefficient of kinetic friction ever. So I don't know what this question is asking, but either way we will do it because we answer what is asked. So we will say this is the graph of UK and FA. Okay, we must always present some form of a topic, and then we do it. So we can call this one the UK, we can call this one the applied force in newtons. So this one is not with anything. So we saw that the force applied here was basically 10 newtons. And we will see that the applied force didn't change. So the other one is 0,19. And then the first one was, let's calculate the first one. The mu k in the first instance, the frictional force was equal to that one. So this is 5 into 9,8. Let's see what that is. So 10 divided by 5 into 9,8. This gives us a 0,20. Okay. So that's the one. So for me, it's really immaterial. There's no relationship between, honestly, these two. It or it is not existent. Hi man, don't go. Hey man. Okay, funa link, man using a free hand. Funa papel. So guys, this is what is expected, but for me, I think the question was on the kinetic friction and the mu k, because these are definitely related. Because from the equation Fk equals mu k times the normal force, seeing that the normal force was constant, it means Fk is directly proportional to mu k. Or one can think of this equation as essentially y is equal to mx. Y being the kinetic friction and x being the mu k. So we see that this is the graph that passes through the origin. Like that. Okay, it's fairly steep, of course, because of its gradient. We can extend this. So we can say this is mu k, this is the fk. And as we can see here, that if we decide this is the story, the kinetic friction when it was smaller, this was 9,5, it went with 0,19. And we can see there that the next one is not so far off. Maybe let's shift this unit a bit. And then this one is 0,20. And we can see this is the graph that we expect. I would believe this was the question, but perhaps an error in the typing or whatever. So if that was the question, which I think this is the one, but again, it could be still this one, but we know that those two have no relationship whatsoever. Because no matter how often we change the slope, or should we say the surface's coefficient of friction, if the applied force doesn't change, it just doesn't change. So there's nothing that happens there. It's a horizontal line. Okay. Either way, guys, whichever it is, we get our 2 marks for the shape and for everything. Right, so that would give us a total of 16 marks, which was not so difficult, I suppose. All right, let's get to question 3. So question 3 says, a soldier holding a machine gun and bullets has a combined mass of 100 kgs. He stands at rest, velocity 0, on ice skating blades, shoes, and fires 10 bullets horizontally within 2 seconds in the forward direction. Okay. So the firing makes the soldier to recoil and moves slightly backwards. Each bullet has a mass of 10 kilograms and leaves the machine gun with a speed of 720 meters per second. Assume there is no friction between the shoes and the ground. Okay, so there we are. Collision, momentum, energy, and impulse. Okay, right, define the term impulse. Again, guys, if you find yourself struggling to do this, it means go and revise all definitions in this topic. So an impulse is basically the product of the force and its time, duration of action in seconds. The force in newtons and its time duration of action in seconds. Of course, if one forgets, just remember the formula. This is the reminder. But in this formula, although we always use the right hand side, for this formula we describe the left hand side. Never attempt to describe the right hand side for this. You will be dead. Again, guys, check definitions so that the answers are exact and you're comfortable with that. Okay, now name the Newton's law that makes the soldier to experience a recoil. Well, it's Newton's third law. Do you see on the MCQs this was suggested? It's coming. As I often said, MCQs, guys, are the window into the structured questions. You just know, if you see something in the MCQs, just know it's coming in more detail in the structured questions. Now calculate the soldier's speed after firing the 10th bullet. Okay, going to use conservation of linear momentum. So we know that P before must be equal to P after. Right? Yes. So before it was 100 kgs times 0 is equal to, now the P, we have lost 10 bullets, so the mass is going to be 100 minus. Now 10 grams is basically 10 divided by 1000. So this is 0,01 times. There's 10 of them. Right? Right. So we will then have lost the mass like that. And of course, this would be the velocity of the men together with the machine gun and whatever they have. And then we will add here. Now the issue here is that, remember, each bullet would have been a 0,01 times the velocity plus a 0,01 times the velocity, and this continues. Now what is common is velocity, so the 0,01 will add up together. All right, so literally here we will have however many these are, and there are how many? 10. So this is going to be 10 into 0,01 times the velocity, which is 720. So this is just the key. Perhaps we want to say this is going to be the mass times the initial velocity. Maybe I had jumped things here. This is going to be mass with the final velocity plus mass of bullets and their final velocity. Great. Yeah, everything looks crazy after all. So a bit of caution here on how to deal with issues. So one must think constructively. All right, so this implies that we've got 0 is equal to, let's do it. So 100 minus 0,01 times 10. So this is 99,9 times the final velocity plus, we've got 10 into 0,01 into 720. So we get 72. Okay. So what is the final velocity here? It's going to be minus 72 divided by 99,9. Of course, this is going to be negative because it's suggesting the opposite direction. But the question said speed, so we shouldn't care what this is. You know, don't know what I'm doing, so I suppose we should make the conclusion. So we just divide this by 99,9. It gives us a minus 0,72 meters per second. We can say therefore, remember we were not asked the velocity, so we can say therefore the speed of the man is equal to 0,72 meters per second in the opposite direction, even though this is not needed in the it's not a big deal. The final statement is the final answer, right? Right, and we cannot present a negative answer anyway. So how many marks was this? 4 marks. Okay, formula, the right hand substitutions, but they were quite hectic, you know. This one, was it really that important? I guess Then the conclusion, of course, guys, everything depends on the overall gymnastics there that were, taken. And we now have to calculate the average force exerted on the soldier by his machine gun. Okay, that's not difficult. That's not difficult. So 3.4, can we squeeze it here? We can try. So the average force here, we know that the force times delta T is going to be the change in the momentum. Now remember, if we're saying exerted on the soldier, we're going to do the change in the momentum of the man. But the problem with this is that the mass of the man is a situation, okay? Is a situation, but again, the force will be both to the man and whatever he has on him. So this would imply that we've got the force. Now the time duration of well, if we fired those bullets, I think the 2 seconds would count as the collision time here. So this is going to be the mass of the man, which is now 9,9, because this is what would be exerted on him. Then his final velocity is 0,72. Of course, we can put it as it is, negative. We can leave it positive. It's up to us, honestly. -0. So I don't understand. Why is this 5 marks though? Why is this 5 marks? It doesn't make sense, I really don't get it. For me, what would qualify for 5 marks is actually the other one, 3.3. See, this question now, guys, is doing its own things, you see. I'm a bit unhappy with it. I am a bit unhappy. Anyway, let's just go on. Whatever is the case, guys, some questions are just not right, They are just not right, because there's always something ridiculous to have to deal with. Divided by 2, which therefore means the force here is going to be minus, so this is 99,9 into minus 0,72 divided by 2. So I'm getting minus 35,96 newtons. Therefore, the average force, we can say, the average force on the man or the soldier, is equal to 35,96 Newton in the opposite direction. Because this time we were told force, not necessarily pinpointing the issue of magnitude only. So it's a vector, we need to consider the direction. Okay guys, I'll mark this one. Yikes, this one is crazy guys. Honestly speaking, I don't understand it. This one is the answer. This and the direction. So 1, 2, 3, 4. I would say perhaps the collision time as well. I don't know. Some questions really are technical rather than labor intensive, you know. It's usually not really a big deal, but it's one of those small little details that we may be missing. So if this is wrong, guys, too bad. I tried. Okay, I really did try. So let's get 3.5. Anyway, one of the bullets hits a block of mass 500 grams, which is resting on a horizontal platform. Now, the impact makes the bullet to be embedded in the block and together slide along the horizontal platform. The block in the bullet system experiences a frictional force of 32 newtons throughout its motion. Right, so it says here, name the type of collision. Okay, there was some deformation here. So this is definitely an inelastic collision. All right, easy one, Mark. So 3.5.2 says, calculate the distance x traveled by the bullet block system before they come to a complete stop. Okay, so now we have a situation. What we need is the velocity of these after the collision, right? Once we get those, we can then know that the change in kinetic energy will give us exactly the work done by the non-conservative force, which is that 32. So we need to use the work energy theorem here. So we will say, fine, we need that velocity. So we know that first of all, P before must be equal to P after collision. So this means the mass of the bullet and the initial velocity plus the mass of the block and its initial velocity should be equal to the mass of the block plus the bullet times the velocity, right? Because they come together. Right, so this implies we will have the mass of the bullet is 0.01, right? It was 10 grams, we were told. And we multiply this with the initial velocity, which was 720, plus that of the block is 550 divided by 8,000. Gives us a 0.55 into 0. It was resting. Is equal to, so 0.01 plus 0.55 times the final velocity. Therefore, the final velocity of these two is going to be 0.01 into 720, all divided by 0.01 plus 0.55, right? So that would be in meters per second. So 0.01 into 720. This is divided by the sum of 0.01 plus 0.55, which is 0.56 actually. Don't know why I had to use the calculator for this. So this gives us a 857 meters per second. Of course, we can see that this is in the forward direction. Okay, very important. Now, this is how they started moving together after the collision. Now we go to the work energy theorem. We know then that work done by friction here is going to be the change in the kinetic energy, right? So this implies that we've got our Fk times delta x cos theta is equal to half m final velocity squared minus the initial velocity squared. So this implies we were told this is 32 newtons into delta x, which is what we want, times the cos of 0. Is it 0? No, 180. Because friction opposes motion, so this is 0,5 into. Now these two are added together, right? So this is 0,01 plus 0,55 into the initial final velocity is 0 squared minus the initial velocity okay. A lot of things to consider here. Great, so we want x, so therefore x is going to be this whole thing 0,5 into 0,01 plus 0,55 into 0 squared minus 12,857 all squared divided by, now this is going to be minus 32, right? Cos of 180 is minus 1. Okay, let's see. So 0,5 into 0,01 plus 0,55, right? That multiplied by minus into 12,857 squared. Make sure the brackets are not going to cause trouble. So I'm getting a 1,45 meters to 2 decimal places. Okay. So wrong or right, we don't care at this point. We have our answer. Okay, so this is quite hectic. 7 marks. Okay, we can mark this. And we can mark the substitutions. We can mark the answer, right? 3 marks. We can give the formula 4 and say 5 with the substitutions and 6, and perhaps this side as well deserves some marks, right? So however the memo is written, we don't care. All we care about is that we got our marks. So 3.5.3 says, how will the distance in 3.4.2 change if the platform is inclined upwards? Will it increase? Will it decrease? Will it remain the same? Well, it will decrease, right? Because there will no longer be just one force against the motion of this object. There will also be the gravitational force in terms of its FG parallel. So the greater the resultant force, then the quicker this object is going to change its kinetic energy. So it will decrease. Right. So easy 1 mark. 3.5.4, it says explain the answer. I'll say on an incline, the resultant force will increase by the addition of work done against the gravitational force. What did I say? The resultant force will increase by the addition of the parallel component of the gravitational force, by the addition of the parallel component of the gravitational force. Okay, and this will, what can we say, guys? It's just 2 marks though. Okay, on an incline, the resultant force will increase by the addition of the parallel component of the gravitational force, resulting in a greater change of the kinetic energy, or should we say a greater decrease in the kinetic energy, a greater decrease of the in the kinetic energy, greater decrease in or of, yeah, that's still good, of the kinetic energy of the system. Okay, therefore the stopping distance will be short. I don't know, guys, there's a lot. Therefore the stopping distance will be shorter. Whatever you say, guys, try to be as clear though, so that there's not too many questions that can be asked after that. Another person can say, with an increase in the resultant force against the motion of the object, this object is going to decelerate faster, and so will stop at a shorter distance. I mean, you can be concise, you can be big, but there's an issue for me though. With an incline, remember something, that with this object here, there is gravitational force straight down, right? And there will be components of force, the vertical ones. So the problem with this issue here is that if we think constructively about the incline, of course, assuming that is the theta there, we know that this is going to be FG. So this is FG parallel, which is perpendicular to FG perpendicular, which itself is equal to the normal force. The normal force is equal to the FG perpendicular, right? But now the problem is that the normal force here is going to be less than the normal force on the horizontal surface. So if the normal force decreases from this equation, Fk is equal to mu k, which is not going to change, times the normal force, which has changed. It means the frictional force will be less than it was on a horizontal surface, you know. And we are going to add some Fg parallel, whose magnitude we're not sure about as well. Now, is there a possibility that the Fg parallel plus this decreased Fk, is it possible to be equal to the Fk in the initial setup? It is definitely possible, depending of course on the angle of inclination. So I feel like this question is not making sense entirely. It doesn't make sense entirely. Because as much as we are adding an extra force, if we don't know exactly the angle of inclination, then we cannot tell exactly how big a change on the frictional force will be and exactly how big the Fg parallel will be. So at the end of the day, it's based on assumptions, because the value of theta here plays a huge role in exactly what happens after all. So these are some of the questions you just wonder if the examiners themselves sat and thought about the implications. But again, it's a mock test anyway, so it's not a real test, so whatever. We could take those marks if we answered everything adequately. If not, then too bad. So we can get our 2 marks there. Okay, try to be clear though in whatever you say, but as you can see, there is some arguing points on this one. All right, so let's do question 4. Question 4 gives us information that a ball is thrown straight up from the ground with an initial speed of 30 meters per second. So there is ball A. So it's going to be thrown up at 30 meters per second. So we are going to choose up as positive because this is VPM. Now at the same time, ball B is dropped. So when it is dropped, it means its initial velocity is 0. Okay? From a height of 15 meters above ball A. Now after some time, ball A and ball B collide at point C and stick together. Okay? And move vertically at a velocity of 5 meters per second upwards. Very interesting. Of course, we know that these would go up, 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 and reach some maximum height together. And then they would go down, 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 down until they hit the ground. So we need to think about that. Okay. Now, of course, here at the very top, the velocity would be 0. Now we're told to ignore air friction, which is good, because if we don't, this whole thing becomes a disaster. First question, define the term projectile. Again, guys, you can do this effortlessly. You are likely ready in this topic. There's usually just 2 definitions here. It's either a projectile or free fall, right? So this is an object that is given an initial velocity which subsequently undergoes motion influenced by the gravitational force only. All right. Of course, some people would like to say free fall, but I would rather discourage you to say that, because you are making the examiner or the marker ask a question again, what is free fall? Okay. But if we are clear that this one has an initial velocity and it subsequently undergoes motion influenced by the gravitational force only, we have done due diligence in this one. All right, easy 2 marks after all. If again a student finds themselves struggling to make that definition come up, it says go back to the textbook and read those definitions in the textbook. Then come back and answer questions. Of course, read a bit more so that you understand. Right, calculate the time at which ball A and ball B collide at point C. All right, what we'll appreciate at point C is that if we have height h, they will be the same height from the ground. Although these will have moved different heights, the ball B will have moved that particular height. We can call h1, can call this one h2, or vice versa. So basically that ball will have moved that height down, right? It will have moved that height down, whereas this other ball will have moved this height h2 up. But at the end of the day, they will be both h2 above ground when they collide. So that's the plan that we need to think about. So we can say, well, for ball A, what do we know? Before we say this, we can say let the height h1 be the height of C, right? Just keep it nice and easy. From the ground. And h2 be C from the top of building. Was it a building? Yeah. Let's just leave it at that. Sometimes it helps to introduce, because we cannot talk of h1 and h2 when we have not essentially introduced them. As you can see here, I messed up. I reversed the 2. So this is h1, h2. Okay, we need to be clear. So we can say here for ball A, what do we know? Well, we don't need time here. So we know that delta y is going to be the initial velocity times time plus half g delta t squared, right? This implies that h1 is equal to, the initial velocity was 30. By the way, we can indicate that we took up as positive. 30 times t plus half into minus 9,8, because this is down, times t. So we can say therefore h1 is going to be 30t minus 4,9 t squared. We can make this equation 1. Right. So we can say also for ball B, what do we know? Delta y is going to be equal to the initial velocity times the change in time times g delta t squared, right? So remember, guys, this displacement is downward. So first of all, to calculate its magnitude, it is going to be essentially 15 minus h1, isn't it? Yes, it's going to be 15 minus h1. But it is itself a downward displacement, so it should be negative, right? So this is going to be minus into 15 minus h1 is equal to, now this one started from 0 minus 9,8 times the time squared. So this implies that we will have minus 15 plus h1 is equal to minus 4,9 t squared. Therefore, we isolate h1, it's going to be minus 4,9 t squared plus 15. This is equation 2. Now, what do we say? These essentially define h1. So these are simultaneous equations. You can say then we understand that 30t minus 4,9 t squared is equal to minus 4,9 t squared plus 15. Now these will cancel as we transpose. So this also implies that 30t is equal to 15. Therefore, t is going to be 0,5 seconds. Okay. Nice and easy. So this one is one of those. Good, challenging questions. Right. Now that we have done our job, what do we say? We get a mark for the formula the first time. We get a mark for the equation. We get a mark for the equation, putting them side by side, and the final answer. Okay. Great stuff. Again, we can check if this is true by plugging this into this equation and plugging it into that equation and see if we're going to get the same answer. Okay. But I can tell it's going to be the same answer because if this is already 15, whatever we put for t here, it's going to make this very small. Not very small, but big, but in the negative. So we'll be taking out from 15. And if we come back here, again, it's going to be a similar thing, you know. Because if we're multiplying by 0,5, this is already going to be 15. Then 15, when we take the same thing out from 15, we should get the same answer. But then it means these equations must be correct before we can say this is true. Okay. But it doesn't hurt to check because problems come without checking things. So 4.3 says, calculate the velocity of, okay, 4.3.1 of ball A before collision at point C. Easy. So we know that basically the final velocity is going to be the initial velocity plus g delta t. So this means the velocity is going to be the initial was 30 plus into minus 9,8 into 0,5, right? Therefore, the final velocity before collision here was 30 minus 9,8 into 0,5. So this is 25,10. Remember, minimum 2 decimal places. This is velocity. It came positive, so this is upwards. Direction is also important here. So we get a formula, substitutions, answer. Remember, the answer must include direction for full marks. 4.3.2 says ball B before the collision. Easy. We will do the same. The final velocity is initial velocity plus g delta t. So the final velocity here is 0 plus into minus 9,8 times 0,5. So the final velocity there is basically minus 4,9 meters per second, which we write as a positive answer 4,9 meters per second downwards. Now, how do we score marks here, guys? It's more of I think it's more of the magnitude and direction. The rest is too obvious, I guess. Right. Maybe let's avoid putting the unit there. Okay, that's easy, guys. Not a complicated question. So 4.4 says, calculate the maximum height reached by ball A and B above the ground after the collision. Easy. So we know that the final velocity squared is equal to the initial velocity squared plus 2g delta y. Right. So this implies that the final velocity, remember at maximum height it's 0. So this is going to be 0 squared equals the initial velocity is 5,1 squared plus 2 into minus 9,8 delta y. We can say therefore delta y is going to be minus 5,1 squared divided by 2 into minus 9,8, which is minus into 5,1 squared divided by 2 into minus 9,8. This gives us a 1,327 meters. Now, what are we going to do to this one? Well, we need to add the height from which they came. So we can say then the height max here is going to be any one of the height formulae that we had above. We can take the simplest, it's going to be essentially minus 4,9, or we can take h1 as it is. I mean, h1 came in two forms, but essentially similar forms. So this is going to be 30 into 0,5 minus 4,9 into 0,5 squared. That was that one. Right. And to this one we add 1,327. All right. So let's see, what is that? This is 30 into 0,5 minus 4,9 into 0,5 squared. This gives us a 13,775 plus 1,327. Right, so we add here 1,327. So this gives us a 15,10 meters. Okay, slightly more than the total height, but it's possible because the other ball had more energy in it. It could have surpassed that 15 meters anyway. So it just barely did because it got opposed along the way. So that's easy. So formula, substitutions, this answer and this one also, and the final answer. Easy, 5 marks. So 4.5 says, how long does it take for ball B? sorry, but for ball A and B to hit the ground after they have collided. Obviously, these ones will be displaced this height down. So I'm going to use advantage of that. So I know that delta y is equal to v I delta t plus half g delta t squared, right? This time we know that this is going to be minus 13,775 equals the initial velocity was 5,1 up times the time which we want plus half minus 9,5, not 5.8 t squared. We will end up with a quadratic here. Okay, so what we have is minus 13,775 equals 5,1 t minus 4,9 t squared. We transpose everything, so we get 4,9 t squared minus 5,1 t minus 13,775 equal to 0. So this is a quadratic formula. This implies that t is going to be equal to minus b plus or minus square root of b squared minus 4ac all divided by 4a. All right. I'm scrambling for time here, guys, so I'm going to just do the substitutions here. Minus into minus 5,1 plus or minus move on. Damn it, this thing, it's moving. All right. Great. So we can say therefore the time is going to be, now we will only choose the positive answer, right? Yes. So we've got minus into minus 5,1 plus into minus 5,1 squared minus 4 into 4,9 to minus 13,775 divided by 2 into 4,9. The first answer is positive. That's the correct answer. So it's going to be 2,28 seconds to 2 decimal places. Remember, the other answer is going to be negative. So we don't have negative time. But if we only had one answer and it came negative, we ignore the sign. But when we have two answers, one is positive, one is negative, yeah, the other one is negative, so we would have to ignore it. Okay, so that's easy. Formula, substituting that correctly. You can say general substitutions there and using the quadratic formula and getting us the answer is perhaps where these marks are. Right. So let's do 4.6. So 4.6 says draw the graph of velocity versus time on the same set of axes for ball A and B before and after collision. Okay. So we can say this is the velocity time graph of balls A and ball B. Nice. So we know we're going to need the y-axis. Nice and easy. Sometimes this doesn't look as vertical as I would want. That is the one. we need, remember velocity time graph, we need to accommodate the negative y-axis here. So this is time in seconds. This is velocity in meters per second. Right. Now this is the origin. Good. So what are we going to say? Before collision, ball B started at 30 and decreased to some 5 point some change. And we know that ball B did its own thing as well. But these ones should be parallel because the acceleration is the same. And of course, I want a vertical line here. Does it look vertical? Not exactly. That's much better. So what I'm going to do is this. Okay, so this is what happens before collision. And of course, we know that that is the velocity this one reached. What was it? We calculated it above, did we? It came out as 25,10. So that was 30 from the beginning. This one started from 0 to this velocity, which we got as minus 4,9. Right? So this is minus 4,9. 0, of course, if we wish. And what time did they take to collide? It was 0,5 seconds. So this is what happened. And then after they collided, almost immediately the velocity had dropped to some 5,10 meters per second. And we can say they then approached maximum height and went about their business until they reached the ground. In fact, I should make sure that the situation is like this. Okay, so this is the case right here. And we just want this to go there. Okay, it looks right to me. Good. So we know that this is the time it took for this to reach the ground. So to 0,5 we add the time that we calculated above, which is 2,28. So we have 2,28, we add the 0,5. It gives us the total time of 2,78 seconds. And of course, we were not asked to calculate the velocity with which they hit the ground, so it's not important. It's not important. Whatever it is, we don't care. We don't care. Okay, guys, so this is it. So maybe we can just show these, that they go there, you know, so that we can avoid issues of saying, where is this? Is it flying? And we know that the velocity that they reach the ground is probably going to be much greater, but on the negative side. But to avoid an outrageous graph, we'll leave it here. Alright guys, so this is it Very nice stuff anyway. So we get a mark for the shape. 3 marks. The extra 2 marks come from where? The time. Right? Maybe the 2 times. Of course, the full marks are only achieved when the overall thing is sensible. We need to see a topic, we need to see the axis, everything nicely labeled. All right, so that was a nice question. 27 marks in the bag. Right. Let's hit question 5. So obviously, guys, I will put the memo and this answer sheet, or should we say this memo? Is it a transcript? It's a manuscript. In the description for those who will be interested to use whatever perspective I have used. Because at times you may not have data to watch the entire video. It can be quite boring at times to watch these videos, I know. So just download the question paper and the memo and you look at it, and if you're fine, that's good enough for you. But if you really want to know the process of going through these issues, the video becomes an excellent supplement to the manuscript. Okay, a steel ball on a swinging rope has a mass of 20 grams. The rope is inextensible and has a length of 3.5 meters, okay, indicated already. Initially, the ball is held at an angle of 45 degrees Celsius to the vertical and swings to its lowest point as shown. Okay, so the question is, guys, what is this? What is this? What is this height right here? That height is the same as this one because it is the chord here. So this is still 3.5 meters. We need to remember that. Okay, so it says define a term non-conservative force. Okay, again, guys, easy things here. If you find yourself struggling, go and revise all these definitions. A non-conservative force is a force whose work done depends on the path taken. Right, that's it. Some are very easy and concise, some are quite challenging. But make sure you understand these rather than you just rattle them from memory. Calculate the gravitational potential energy at the initial position relative to the lowest point. So how are we going to do this? Well, it means we need to cut this like so. Right at that level, we know that this is going to be vertical to our things. And if we look at this triangle, this lovely triangle is a right-angled triangle. So we are interested in knowing this height above ground, right? But we can find out what this height is. Let's call it x. So it would mean this would be the entire length of 3.5 minus this, because this is going to be 3.5 minus x. That's what it means. Okay, good. So that's the plan. So again, guys, because this is gone, it is nicer to reproduce this sketch in the diagram. I'm not going to do it because I've already done it there. because most likely the answer sheet will not have the sketch, but if it does, use the sketch. So we will see here that essentially we want the gravitational potential energy at this position there. So first of all, we can say the height at the initial position. Please state it. This is h. We said it's h. Is such that we know that basically cos 45 degrees is going to be adjacent, which is x, over over hypotenuse, which is 3,5. This is over 1, right? So we cross multiply. We'll say that therefore x is going to be equal to 3,5 times cos 45 degrees, which is 3,5 times cos of 45. Okay, this one is giving us a thing that I like. It's 7 root 2 divided by 4 meters, right? We can say therefore our h is going to be 3,5 minus 7 root 2 over 4. Right, so we have 3,5 minus 7 root 2 over 4. So to avoid anything, we will leave it as it is. It's 14 minus 7 root 2 over 4 meters. Okay, because we don't want to end up rounding off too soon. So now what do? We can say then we know that potential energy is going to be mgh. This implies that EP, the mass, is 20 into 9,8, and the height is 14 minus 7 root 2 all over 4. Right. Therefore, EP is going to be 20 into 9,8 into 14 minus 7 root 2 over 4. Okay, so this gives us a 200.92 joules to 2 decimal places. Nice and easy. So this was a bit. So essentially what I'm thinking, finding the value of x is key and finding h is key. Then substitutions into the formula and the answer. Again, substitutions are maybe a bit more weak, but that perhaps easy 4 marks after all. Right, so we have 5.3. It says, is total mechanical energy conserved? Right, yes or no? Look guys, these are the questions that are an abuse honestly to students, because normally we need to know if we have to ignore air resistance, but now there's no mention of ignoring air resistance. And the worst part is we've got a non-conservative force, which is to suggest that there's air resistance in here. But then we're not too sure whether we need to consider this or not. Sometimes when I get to these kinds of problems, I read along, skim all the questions and see if there's any suggestion that I may have had to ignore this. So let's say we come down and say, okay, it says explain your answer, fine. Calculate the speed of the ball when it has traveled halfway along its path from its initial position to its lowest. Again, no mention of air resistance issues here. So how do we do this? We will not be able to do this if we don't ignore, because we need to use conservation of mechanical energy here. So this says this question is related to how we answer that question. All right. And 5.4 says a resistance force R is now applied. Can you see? So this is to suggest that, but again, this force could have been applied to already an existing force of air resistance. So you start to be like, okay, these questions were a bit vague. And vague questions are truly an abuse to students. They should be avoided. Again, I don't know. It's just my take. Now, the total mechanical energy, here we're going to then suggest that it should be conserved, because we can't answer here if we haven't said so. So, I mean, can you see, guys, you have to base your answers on assumptions now. We can say yes. And that's it. So 5.4 we can say with the assumption, because we need to state this, with the assumption that air friction is ignored, the total energy will be conserved as there will be no external resultant forces. And by the way, we can say NB FG is a conservational. What is it? Is a conservative force. Okay. Of course, one can put this in brackets just to showcase that yes, there's FG acting here, but it is a conservative force, so it doesn't hold any issues, because sometimes to say there will be no resultant force, it's ridiculous. There is actually a resultant force, Fg, but Fg is a conservative force. All right, that's how I would put. But again, guys, it would be based on the assumption, which I feel is incorrect, because we should never have assumptions in an exam. But what do you do when the examiners do a ridiculous thing themselves? You do a ridiculous thing too. Anyway, folks, this is just 2 marks. So yeah, I guess this is just 2 marks as a whole, however one wants to look at it. So we have 5.5. It says, calculate the speed of the ball when it has traveled halfway along its path from its initial position to its lowest point. Okay, so that's easy. So we know that basically the mechanical energy, E mag top, let's just say EM top, is equal to EM bottom, right? Using the conservation of mechanical energy. So at the top, we only have potential energy. But again, we can just show this and say mgh plus half mv squared is going to be mgh plus half mv squared. So this implies we were told this is 20 times 9,8. And of course, here at the top, by the way, we have already done the calculation above. So this is 200,92 plus half of 20 times 0 squared equals, this one is going to be 20 into 9,8. Now the height is going to be 50% of what we had. So this means we're going to say this is 0,5 times 14 minus 7 root 2 over 4, right? Yes. Plus half of 20 v squared, right? This is what we have. Interesting things. Okay, now we continue. This implies that 200,92 is going to be equal to, let's get this one down. So this is going to be 20 into 9,8 into 0,5 into essentially 14 minus 7 root 2 over 4. Just put it on the calculator as it is. It makes life a lot easier. So this is basically 100,462 to 3 decimal places plus 10 v squared. This is what we will have. You can say therefore v is going to be the square root of, we're going to have 200,92 minus 100,462. This will be divided by 10. Right. Okay, square root of 200,92 minus 100,462 divided by 10. This gives us a 3,17 meters per second. Equals to 2 decimal places minimum. We can do 3, but 2 is cleaner. Alright, not a very difficult question after all, but I am not very happy with the fact that the opening statement did not tell us enough to answer 5.3 smoothly to 5.4 to 5.5. We had to use the assumption, and this is unfair. Either way, nobody cares, right? Yeah. So that, cool. This calculation, cool. The general substitutions, cool. Final answer, cool. And of course, I suppose that, cool. There should have been 4 marks after all. Anyway, we are done with the question. So this is 5.5, okay? Now let's look at 5.6. Again, there's a typing error there. Now, a resistance force R is now applied to slow down the motion of the steel ball, as shown below. The speed of the steel ball at its lowest position is 4 meters per second. Okay, that's fair enough. It increased by a bit from 3, so we know we're not really far off. So the question says, calculate the work done against the resistance force as the steel ball travels from its initial position to its lowest position. Again, you see, from initial to lowest. Alright, this is work done by non-conservative force. Work done by non-conservative force is going to be equal to the change in potential energy plus the change in kinetic energy. Right. So this implies that work done against or by this frictional or resistant what? Resistance force, Simon. Chin. 10 go. Now we know that at the bottom or in the lowest position, the kinetic energy is 0. Potential energy is 0. So we'll subtract the initial, which was 200.92, right? Plus the kinetic energy is a different story, so it's going to be half of 20 into the final one is 4 squared minus the initial one was 3.17 squared. So I have used square brackets. I might as well just do it. Okay, we can say therefore the work done by R is this one. So this is minus 200.92 plus 0.5 into 20 into 4 squared minus 3.17 squared. Wait. This is 0. This is 0. Because we said initial position. Big mistake here. Alright, so this is minus 200.92 plus 0.5 into 20 into 4 squared basically. So we see that it's a negative work done. This is good. 40.92 joules. We can say therefore work done against resistance force. Nkosi yami don't google. Ke eng jwale ntwena? Force R is equal to 40.92 joules. So the answer must be presented positive, guys, as the final answer. Do not present a negative answer. Alright, formula. Guess this calculation and the general substitutions and the final answer. Easy 4 marks. Taking some quite controversial 18 marks, right? Because 5.3, 4, and 5 is questionable. Either way, we move on. Question 6. Now, question 6 says an electric motor drives a turbine that pumps water vertically upwards from a dam to a reservoir at reservoir 50 meters above. Okay, the dam. Now the pump delivers 1,200 kg of water in 2 minutes. Okay, and the water is delivered at a speed of 12 meters per second at the reservoir. So this is all that we see. Now the question says define the term average power in words. Easy stuff. 6.1, we can say it is the rate at which work is done, or we can say it is work done per unit time. Since we use the word average, you can say it is the average rate at which work is done. Either way, guys, easy 2 marks. This one is too simple to complicate. Right. Says calculate the average power of the electric motor. Remember, of the electric motor. Now if we draw a free body diagram here, there will be a force by the motor, which is the applied force, but we are pumping this against gravity. So there is Fg. Of course, if we're moving up, it means that one is greater than the gravitational force. Right, so we need to know what is this force. We can do that, or we can just do work done by a non-conservative force and then calculate the power. So why do we need to struggle? So we can do it. So we can say, well, we need the work done by non-conservative force here, which is the electric motor. It's going to be change in potential energy plus change in kinetic energy. So this is going to give us the change in potential energy is m g h change, literally, plus half m final velocity squared minus the initial velocity squared. By the way, this W must be a capital letter W, right? This is going to be the mass of water, 1200 into 9,8 into the height is 50 minus 0 plus half of 1200 into the final velocity. This is 12 squared minus 0. It was initially at rest, so therefore the work done by the non-conservative force is 1200 into 9,8 into 50 plus 0,5 into 1200 into 12 squared. So we get 674. So this is 674,400 joules. We can say then we know that power is going to be the rate at which work is done over time. So this means the average power here is going to be 674,400 divided by, we were told this is 2 minutes, now this is per second, so there's 60 seconds in a minute, then we multiply that by 2. So we then divide this by 2 into 60. It gives us a 5,620 joules. Nice and easy. Not joules, not joules. Watts. This is a watt. Is it watt or watt? It's a watt. Watts. Is it watts? Yeah, I think it's better that way. Okay, guys, so this is how I suppose this should be done. Sometimes you don't want to beat about the bush. This is important. That and that is important. That is important. Easy 4 marks. And this conversion is good. That with the unit is good. Another student could approach this using the resultant force. Okay, so we can look at that as well and say, look, if we want the resultant force first, we can do it. Why? Because we saw that the water accelerated from 0 to 2 meters per second. We know that F res equals ma. Now we know that the force applied minus double, what is Fg, is going to be MA. Then we know that the force applied minus 1200 into 9,8 is going to be 1200 into acceleration is change of velocity, so this is going to be 12 divided by 2 minutes, which is 2 into 60. Okay, so we're moving fast here, so we can say therefore the force applied is going to be 1200 into 12 divided by 2 into 60 plus 1200 into 9,8. So this would be 1200 into 12 divided by 2 into 60 plus 1200 into 9,8. So this gives us 11880 newtons. We can therefore say now the power is going to be the rate at which work is done. So the work here is going to be the force, which is 11880, times the displacement, which is 50, times cos of 0 degrees, all divided by 2 into 60. Let's see, 11880 into 50 into cos of 0. So all of that is divided by 2 into 60. This one is giving us a 4950 watts. Okay. Again, usually these calculations, depending on the approach, have a tendency to not be exactly 100%, you know, because there's other issues that are getting involved or getting in the way. But for me, 4,950 is very close to 500 at least, so it's quite comparable. I would suppose that approach should be marked correct as well. So that is the story, guys. Otherwise, it's not a very difficult question to answer. So that was a fairly easy 8 marks to score. Right. So let's move on to question 7. Question 7 says, a sound wave of frequency 400 Hz is traveling through a medium where the wavelength of sound is 0.85 meters. A listener moves towards the sound source at a velocity of 2 meters per second while the sound source is stationary. All right. That's good. So it says define the term Doppler effect. Okay. Again, guys, easy stuff. A student should know how to do this effortlessly. It is an apparent change of frequency as observed by the listener due to relative motion of the sound source and the observer or the listener. Okay, so it is an apparent change of frequency as observed by the listener due to relative motion of the sound source and the listener. In fact, guys, just think about it. If, let's say, for example, the source was moving, let's say the sound source was moving. Say the sound source is moving away as well. So this guy is moving towards, that one is moving away. So let's say the sound source was moving away at 5 meters per second. So what would you do? The source is, the listener is moving towards, the sound source is moving away at 2 meters per second. So what would be the case here? We have to stop one using relative velocity. So it is in the definition, right? We just need to stop the other one. So how do we do it? We can do whichever we like. Of course, the best is to stop the listener, right? So if we stop the listener, that means we're going to say 2 meters per second minus 2 meters per second. Same for the sound source. It was moving at 5, then we subtract 2 meters per second. So this would be 0. This would be 3 meters per second. So this would be the velocity, because remember, each time we perform these calculations, one must be stopped and one must be moving. So remember, we will not always be given a scenario where the other one is stopped and the other one is moving. Of course, it may be that it is a must according to some rules, but if it was given both moving, because in grade 10 you learn about relative velocity, you should be able to do this without a flinch. So sometimes if they are both moving, we stop the other one, and if we stop the other one, we do the same thing to the other one, and the resulting velocity is what will help us to do things. Okay, that was just a thought, because I did discuss this with my students as they were preparing for paper 1. So I know it's not that likely to come, but it's something to think about. Great, so 7.2, we have to calculate the speed of the sound in the medium. This is easy. V is equal to frequency times wavelength. Basic grade 10 calculation, honestly. So this is 400 into, the wavelength is 0.85. Therefore V here is 400 into 0.85, it's 340. So this is the sound in air. To make this question interesting, one would ask, identify the medium. Then it would be quite a challenge, because it'd be like, how am I going to do it? Just check what the value is. If it is 340, this is the sound in air. This is what we accept. It's a constant. Great, guys. Okay, so that's it. Formula, answer. Great stuff. So easy 2 marks. Okay, 3. Okay, substitutions. So this is 7.3. It says determine the frequency of the sound waves as detected by the listener moving towards the sound source. This is the Doppler effect equation. So FL is V plus or minus VL divided V plus or minus Vs times that of the source. This implies that the frequency of the listener is 340. If we're moving towards, we're going to add plus 2. Right. Over 340 times 400. Okay, very easy calculation over there. So we've got 340 plus 2 divided by 340 into 400. And of course, if we're moving towards, we expect a higher frequency. 402,335 hertz is slightly higher than the emitted frequency of 400 hertz. So this is good. So formula, substitutions, answer. But I think the substitutions are mainly that part right there. 7.4 says determine if the listener moves away, all right, from the source at the same speed, okay, what frequency would they detect? Again, same calculation. Frequency of the listener, V, unanimous. So this implies FL is 340. This time we're going to take away that velocity so that we have we have a proper fraction to then give us a lower frequency overall. Therefore, easy, 340 minus 2 divided by 340 times 400 is going to be 397.65 hertz to 2 decimal places. Nice and easy. So this time here is just that and the answer, right, is what matters. So in easy 10 marks here, they kind of eased up on the students. But I can tell you guys that Doppler effect calculations are fairly easy to handle. They can just be complicated by the ugly numbers that sometimes one can arrive at. But don't shy away. Anything that is an equation, simultaneous equations can apply. So we've got question 8. So question 8 says two charges X and Y with magnitudes of plus 8 microcoulombs and minus 2 microcoulombs respectively are 6 meters apart. Sketch is shown. State Coulomb's law in words. Okay, again, easy stuff. We know that the electrostatic force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Some people say between their centers. Doesn't really matter. Again, guys, the direct proportionality to the product and the inverse proportionality to the square of the distance is the key part of this definition. Right. 8.2 says a third positive charge, fact of the matter is that it's positive, is placed along the horizontal line with charge X and Y such that it experiences a zero net electrostatic force. Explain why this charge Z cannot be placed between charge X and Y but must be placed outside, because it would be attracted to the negative charge and would be repelled by the positive charge. Easy. It would be attracted by the negative charge Y and repelled by the positive charge X such that it experiences a positive, maybe let's just say a non-zero resultant force. Now when it doesn't, it will start moving, because remember we were told that we want this to be stationary. So if we want this to be stationary, it has to be outside. Now the question is, can it be this side or should it be that side? Well, we don't know. So it can be on either side, honestly speaking, but what I'm looking at is that this magnitude is fairly small compared to that magnitude. So the best place would be here, right? Because if we place it here, this is quite big. It will push it away so that it's far out of reach from this one. At the same time, we know that these two attract anyway. So they will be too busy attracting each other and ignore that positive charge in a way. So, yeah. It's quite a strange thing, right? Yeah, that's it. But I think if we say that it will experience a non-zero resultant force, that is just good enough. But again, one may ask why. So this is why you would want to go about explaining this properly and suggesting that this would be attracting it while the other one is repelling it. At the end of the day, it is what it is. So the essence of it all is the non-zero resultant force. So easy 2 marks here. Nice. So 8.3 is saying calculate the distance where charge Z should be placed so that the net electrostatic force is 0. Because logically I would accept this position. Although one could still accept that position, but because this charge is too great, it means the distance would have to be slightly longer, I suppose. It just depends on, honestly, how one wants to look at it, because this is just how it's going to work. But now if this is too far, will this one reach in terms of the pull? Yeah, in principle it will, I guess. So let's see what is the story. So we're going to use this one, guys. So let's just call this distance between them, we're going to call it D. Okay, so that's good. So now when we answer this, we need to show the sketch. I'm not going to show it, but please see the sketch. Because this is very important to highlight what happened. Of course, normally these diagrams are not provided, so one would have to draw the sketch before attempting to answer. But now we're going to say, fine, we know that the electrostatic force due to essentially X, due to X on Z plus the electrostatic force due to Y on Z should be 0. That's what we are told. So this means this is KQX QZ divided by R squared plus KQY QZ divided by R squared must equal to 0. So this is 9 times 10 to the 9 into that of X is 8 times 10 to the minus 6 times QZ divided by the distance between these two is going to be basically 6 plus d all squared plus 9 times 10 to the 9 into, this is minus 2 times 10 to the minus 6 times qz all divided by, this is just d squared. Should be 0. Right. So this implies that we can just calculate these things now. So we have 9 to the 9 into 8 times 10 to the minus 6. It gives us 72,000 qz over 6 plus d all squared. This becomes negative. So this is 9 to the 9 into, this gives us minus 18,000 qz over d squared equal to 0. So what I would do, I transpose the one hand side. So this is 72,000 qz divided by 6 plus d all squared equals 18,000 qz divided by d squared. Since I have fractions, I can take the square root on either side just to avoid a quadratic situation here. Right. So what do we have? So we will end up with square root of 72,000. It gives us a 268, I'm going to take 4 decimal places here. So this is going to be 3282 root qz, of course, all divided by essentially 6 plus d equals, we do the same here, square root of 18,000. Okay, this one gives us 134,164 to 4 decimal places times the square root of qz divided by d. Right, that was a question, We then cross multiply here. So we will end up with 268,3282 root q z times d equals, this one is going to be 134,1641 root qz times d plus that times 6. So we've got 134,1641 times 6. This gives us 804,9846 q root q z. Okay. So what are we going to do now? The ones with the d's must take care of each other, right? So we end up with, so I'm gonna take this and say minus 268,3282. So So this gives us a 536, 6564D is equal to, I made a mistake here. I didn't do the right calculations. I actually took that 804. It's not supposed to be the 1. So I'll say 268, 3282 minus 134, 1641. It gives us a 134,1641 square root of QZ is equal to 804,9846 square root of Q. So this is times D, by the way. So therefore D will be the division thereof. So this is 804,9846 divided by 134,1641. So this gives us a 6 meters. Yeah, again, the questions on electrostatics are annoyingly complex because of the numbers that we have to deal with. So it's usually big numbers or very small numbers. So this is it. This is it. So essentially, guys, this is the 1. This is the 1. Right. So this should be 6 meters from this one. Okay, it should be 6 meters from that one. From that one. And we can see, guys, if we chose this side, but if we chose this side, surely because this is big, this would be also bigger. You know, it wouldn't be 6. So, but again, we made a choice and we just have to stick by it. Again, this is not a very nice question in that there's 2 possibilities. So how do you explain each one? Because each one will yield different answers. I guess whichever you chose, you stick by it, and that should be fine. So this was 6 marks, okay? We can say here, well, the substitutions in each are key, equating this to 0, key, the final answer, key 1, 2, 3, 4. Now we're scoring 6 marks. Okay. I guess this would be the 5th mark, and perhaps writing the rule, I guess. Doesn't make sense anyway. Should be 5 marks at least. Right, that's it, guys. So now we have 8.4. 8.4 says, the polarity of charge that now changes to a negative. How will the equilibrium shift, right towards X or towards Y? Now, depending on our choice right here. If we make this negative, since this charge is quite big, we may have to move this maybe more towards this one now so that it can repel it strongly while this one pulls at it strongly. So I would say towards Y, seeing that we chose the other way. Again, this question is saying something about this too. It depends on the choice made up there. So again, it's quite an unfair type of questions. I don't really like them because the choice you made at the top influences what happens. So this means there's either towards X or towards Y, depending on the choice one made. It's crazy, isn't it? And then it says explain the answer. Right, 4 marks. Yo. I can go. Okay, this is because, what do we say? We need a stronger force of repulsion by Y, whereas we need a much stronger force of attraction by A. so that these two can be proportionally equal. So we can just say, well, since Z is now negative, it will be repelled strongly by charge Y, and will need to be strongly attracted by X. Therefore, Z should be slightly closer to Y to achieve this effect. Okay. Yeah, that's it, guys. I would put it that way. But again, you can argue that if you push it away from Y, then this can happen up until the repulsion is equal to the attraction by the other one. So, I mean, it's a very ridiculous question in my opinion. Either way, any answer can be enough here. So, whatever you say, guys, as long as it makes sense. But I really don't like that 8.2. In fact, this question 8. Because 8.1 is the only thing that is fair here. Anyway, whatever, guys. Sometimes I may actually be missing the point, thinking that I've got it. Of course, barring any issues, we should be scoring those marks. Okay, let's kick this thing to the end. Question 9. So I told you the circuit diagram below shows a battery with an EMF of 120 volts. So this is EMF, okay, and with an internal resistance R. The reading on the ammeter A1 is 1,2 amperes, and on ammeter A2 0,40 amperes. The resistor R has a resistor greater than 80 ohms, okay? Right. Now, following the conventional current, it comes off the positive terminal, moves across the circuit, gets to this point, it splits into that segment and that segment. And here, they come together and the main comes up and the circuit is complete. Okay, a very simple circuit here. So question 9.1 says state Ohm's law. Again, very easy stuff. We know that the potential difference maintained between two ends of a conductor is directly proportional to the current in the conductor, provided the temperature is kept constant. Of course, what is the significance of keeping the temperature constant? it keeps the resistance constant, because with a higher temperature the resistance increases, lower temperature the resistance decreases. Okay, that's about it. Nice and easy, guys. Again, please don't lose out on definitions. You can lose out everywhere else but not this. Without a calculation, explain why the power output of the resistor R is smaller than the power output of resistor whatever. Of course, we can see that here the current is greater than 1, so this would make a proper fraction, sorry, an improper fraction against what is a proper fraction. This is less than 1, so we can just say, well, the current because I'm telling you palaka send lambile ki lapile impa ka sepedi ha ba lapile ho tshwa re ba kgathetse jale he rona ba tlaetseng Sesotho re tseba hantle gore ha re o lapile o batla dijo ntate ke batla tsona hona tjena impa ke na tsona ka mona ka tlo ke tsebe ke tlo ja anyway tlo founela bana ba ditoro tse rekisang dijo ke body rib and stuff re ba founela ba ntlisetse dijo mpa ke di rate he dijo tsena tsa teng ga di tsamaya hantle mmeleng mona. Anyway, let's do it. Without a calculation, we can just say the current through the 80 ohm resistor is greater than 1, whereas the other resistor has a current less than 1. Has a current, askes Pali signs, less than 1. Therefore, the power will be greater for the 80 ohm resistor. Since we know power is I squared R. Done. So it will be greater for the 8 ohm resistor, since it is such that power is this. So this equation helps us to know this, because when this thing is less than 1, the square becomes even smaller, so we will take out. Whereas when this is greater than 1, the square becomes even bigger, so we will be exponentially increasing. So that's the idea right there. So again, guys, very key stuff, comparing the currents and the equation thereof that signifies the issues here. So this is 9.3. Okay, maybe let's answer it differently. So 9.3 says calculate the internal resistance. Easy. We need the V parallel here. Is going to be IR. So this implies that V parallel is the current is 1,2 into 80. So therefore V parallel is going to be 80 times 1,2. Gives us 96 volts. You can say then we know that the lost volts is going to be I times the internal resistance. Now this is going to be 120 minus 96 equals, the current is the sum of these two. So this is 1,2 plus 0,40 times R. So therefore R is 120 minus 96 divided by 1,2 plus 0,40. Okay, easy. 120 minus 96 divided by 1,2 plus 0,40. This gives us 15 ohms. Fairly easy. So the one that answers the question is key that calculation matters. How many marks were we giving? This for me is also very important. And the answer, and that one is too easy. That was 9.3.1. Okay, so that was supposed to be 9.3. Please guys, make sure that you number things correctly. 9.3.2 says the value of the resistor R. Easy. V parallel is equal to IR. This one, we saw that this is 96 equals 0,40 into R. Therefore, R is going to be 96 divided by 0,40 gives us 240 ohms. And indeed, this is greater than 80. So I suppose substitutions and the answer here. (9.4) says if the 80 ohm resistor is replaced, okay, we're replacing this one by now a 120 ohm resistor. How will the reading on the ammeter A1 be affected? Of course, if we increase the resistance, the current there is going to decrease. So it will decrease. Right, easy 1 mark. Answer here is what is the story. Okay, all right. Okay, so it says explain fully the answer in 8.1.4. So what I would say is that the ratio of resistors is going to be 120 is to 240, which is going to be equal to 1 is to 2. We can say then the ratio of currents is going to be 2 is to 1. It's the opposite, which implies that A1 would be 2 over 3 into 0,40 plus 1,2, because it's still the same battery. It will deliver the same current. Therefore, A1 is going to be 2 over 3 times this 0,40 plus 1,2, because the total current will not change since the EMF hasn't changed. So this is 1,07 to 2 decimal places. So this is it, guys. So sometimes an explanation, remember, can be a calculation. As you saw there, there's an etc. So you can decide to show a calculation because there's no one who said how you're going to do it. So we can say after this, by the way, we can say therefore the current through A1 will decrease, because it's very important to make that conclusion clear. The calculation was a means to an end. Right, so easy stuff. So I would rather we show all of this shenanigan right here. This is the essence of it all, and the valid reason to explain this. Of course, there's many ways one can go about it. You can say if we increase the resistance there, the current should decrease, right? Yes, if we keep the same voltage V parallel, which is likely to be the case because that's the only resistor on the outside. So the lost volts are going to be the same for the same current. We can use that issue here. So look, the lost volts, same internal resistance, same current delivered by the battery. The lost volts will be the same, meaning V parallel is going to be the same. So with the same V parallel but an increase in the resistance due to Ohm's law, the current should decrease. So one can also use Ohm's law here, essentially. So you're not limited to one way of thinking. I'm just trying to demonstrate that to you guys so that you understand that this is not about cramming your way through, but it's about working your way through. So this is a total of 150 marks, guys. If we did not make any errors, as you could see, we kind of choked along the way because some questions are vague. Maybe we are missing the point, or they are just terrible. At the end of the day, guys, never give up. Just keep doing what you can do best. Remember, the question has already been asked, so it's unlikely to be asked again in the same manner. So just remember, look at what can make it work for you. Answer it that way, because the next question might just come in that state, because this one has already come out in the state that it has. So chances are it's never coming back the same way, except for a few issues. I mean, I looked at the chemistry paper from Gauteng yesterday, I think. It actually looks exactly like a question in 2019, I think November 2019 or May, June or something. And I discussed this question with my students. If that student is in Gauteng, she must have smiled, because it was exactly the way those questions came, but again, slightly tilted about. So they asked the reverse questions instead of the forward questions that were asked initially. And I always tell them that if you work on a question paper, just think of the opposite way that the same question can be asked and how one would go about answering it, because that's the likely way it's going to come. Unless you're really lucky that it comes exactly the same way, already you would know what to do. But perhaps if the question is controversial, then it would be quite a contentious issue. At the same time, you have seen what needs to be done. But if you think about how else you would answer questions that are constructed from the same structure, but perhaps slightly asked, differently asked, what would you do? Then that thought becomes your way of going through issues much easily. Anyway, guys, I hope the video was to your satisfaction. Whoever asked it, I forgot now who's the person who asked for it. And I also hope that it finds you well within time before your next exam, because it may be helpful to revise issues and also to understand the technical aspects of physics paper 1. Otherwise, guys, I'll see you next time. Goodbye.